So let's begin with the first paper, that is simulation of road traffic at light control intersections with Antonín Kavička from the University of Pardubice, Czech Republic.
Okay, thank you. I would be happy if we can start with playing the video. Where is the presentation? And then I'm certainly ready just to answer your questions.
So do you want me to share it for you?
Yes, yes, please, please, you can start the video. Ladies and gentlemen, let me present our contribution called Simulations of Road Traffic at Light Control Intersections. My name is Antonín Kavička and I'm from the Faculty of Electrical Engineering and Informatics from the University of Pardubice in the Czech Republic. My co-authors of the contribution are mentioned on this slide as well. Let me make several comments to the expected presentation structure. At first, I will make some introductory comments. Then I will say several words about the light control intersections. After that, I will pay attention to the motivation of using road traffic simulations. And the main focus will be on the case study, where the selected segment of road network of our university city will be used. At the end, I will make some concluding remarks connected with recommendations of using simulations of road traffic. Introduction is connected with some kind of motivation. It's a typical task of city councils' agendas, just to organize planning of road infrastructure and road traffic within urban areas. In this context, these solutions are expected to bring safe, smooth, and ecological road traffic on urban roads. Within the frame of urban roads, there are very important traffic points. In this case, light control intersections, which can make, let me say, some kind of traffic control of the road networks. And light control intersections are strongly connected with signal plans. How to produce the signal plans? They can be used several analytical methods for producing signal plans. One of them widely used is called saturated flow method, which was used also within the frame of our case study. And that saturated flow method offers for, let me say, different parameters, different signal plans. Light control intersections can apply static or dynamic traffic control. Static control means that we have just one signal plan, which is applied to traffic control. However, dynamic traffic control expects switching between several signal plans, reflecting the current intensities. What about road traffic simulations? Road traffic simulations in this case are widely used for investigations of variants. I mean, variants of infrastructure layout or variants of traffic flows. And in our case, it's very important that they are investigated also the variants of signal plans. road traffic simulations support simulation-based optimizations. In this context, it means that are made comparisons of different variants, and relevant optimization criteria are applied. Examples of those criteria can be mean delay times of the vehicles or total emissions produced by the vehicles. Let's jump to our case study. Our case study is connected with city center segment in the city of Pardubice. You can see it on the screen. This segment is composed of 3 intersections. Intersection T1 is a central intersection, it's a light control intersection, and the smaller intersections T2 and T3 are here as well. Those intersections are interconnected by typically multi-lane roads. The main task is just to investigate the different signal plans applied within the frame of this, it means T1 intersection. So, applying road traffic simulations, I can say several words about the simulation experiments. So, simulation experiments are connected with just one variant of road infrastructure, just presented before. Simulation experiments applied 100 replications for each scenario. It was used the simulation tool EMSS, and the simulation step applied was 0.75 seconds. The focus was on the rush hour between 3 and 4 p.m. and each simulation run at first applied warming up phase for 20 minutes of simulation time. As an output from saturated flow method, 2 signal plans were considered. We call them scenario 100 and scenario 120, which reflect, in fact, the values of cycle lengths at the light control intersection. It means the first variant was 100 seconds and the second variant was 120 seconds. Of course, a lot of parameters have to be set up for the simulation model. Here is just one example. You can see here origin destination metrics for private transport, where the flows between selected points of the network are presented. The values here reflect number of vehicles per hour within the frame of those flows. Just before making final investigations, simulator was calibrated. It means within the frame of verification and validation stage, they were observed the characteristics of the simulation model behavior, and it was mainly substituted the initial setting of reaction times of drivers, which was set up to 1.35 second value, but after observing the behavior of the model and comparing with reality, it was substituted 1.5 second, which then realistically reflected the behavior of drivers in the city. Both scenarios bring some results. So you can see here in the table, in the first column scenario 100 and the second scenario, the second column scenario 120. The most important indicators observed are highlighted. So mean delay time, mean stop time, and total emissions were considered. The results were also demonstrated by means of heat maps, where the intensities of the flows can be depicted and demonstrated. What about results evaluation? Applied optimization used minimization of mean delay time and mean stop time. And from this point of view, scenario 100 represented a preferred variant because the values of those indicators are better than in the second scenario. Total emissions are very similar for both scenarios. So, concluding remarks are as follows. It is recommended to apply combined procedure for studying and optimizing the systems with light control intersections. And this combined procedure is composed of 2 points. At first, there are formed signal plans with the help of analytical methods. And second, those plans are then verified or investigated their application using traffic simulations. And then those variants are evaluated and recommendations are published. Okay. Thank you for your attention, and if you have some questions, I would be happy to answer them.
Thank you very much. If there are some questions. Okay, well, for me it was very interesting since I work with simulation and optimization. And I have a question with how did you perform the optimization? With which software?
As I said before, the applied approach is based on simulation-based optimization. So it means the simulation itself does not offer automatically optimal results. So we have to suggest, let me say, sophisticated series of simulation experiments. Then, according to optimization criteria, the relevant indicators are observed. And after that, the variants with the, let me say, best results are depicted or selected as at least suboptimum solutions. So that's the point. And probably another remark is that, as was presented at the last slide, those simulation-based optimizations are strongly interconnected with the first step. It means there are applied analytical methods for first setting up the length of signal plans. So it means the selected methods of operational research are as a first step, and then the simulation starts investigating, and then the optimization process is finalized. I don't know if it's enough to my answer, so if not, you can ask more.
Oh, no, it's fine. It's fine. Thank you very much. And well, let's continue with the second paper. Zdeňka Stojaspalová, again, University of Pardubice, Czech Republic.
Yeah, thank
Sorry,
you.
I don't know how to pronounce your names.
Don't worry, it's hard even for Czechs. So.
Besides, I am in the other side of the world. I am in Mexico City. Mm-hmm. So for me, it's very, very early. So.
Yeah, it's not typical.
Yeah. Well.
Okay, and can you please also share our presentation?
Sure.
Yeah, thank you, Mohai.
Dear ladies and gentlemen, I am Zdeňka Stojaspalová and I am a PhD student at University of Pardubice in Czech Republic. I would like to talk about simulation assessment that I did together with Josef Bulíček. The topic, as you can see, is distance of bus stops from junctions. Let's start with the reason for choosing this topic. Maybe also in your city you can see the bus stops in the driving lane, which are located near the junction. If several factors are mixed, such as the high traffic intensity, the short interval of public transport buses, and so on, the capacity of the junction may decrease. In the worst case, traffic will collapse. We just wonder whether we can somehow describe these dependencies in a general way or not. Research was based on 4 types of bus stop located in 4 cities in the Czech Republic. In the figure, there is also information about the population. So as you can see, we have chosen a variety of places with different sizes and also different transport services. Now let's turn to those specific types of bus stops. A represents basic case without signaling plan. B represents interaction with roundabout, where vehicles are strictly obligated to stop behind bus at stop. C could be marked as most common situation. D represents more complex nodes with rush traffic with some specifics, like reserved driving lane. Having finished this part, I'd like to turn to the next point, inputs and outputs. Inputs characterize operational features of assessed situation. For us, inputs are distance of bus stop from the junction, time difference between bus services, time of blocking of a driving lane, and intensities of traffic flows. And as the outputs, we considered average vehicle delay, number and ratio of delayed vehicles, average or maximal queue length, and also we counted cases when queue was longer than distance from junction to the stop. With this all, we have come to the following topic, methods. We conducted a set of experiments to get as general results as possible, not just to model the state-of-art situation only. 2 methods of simulation were chosen. First approach works via microsimulation software PTV Vissim. Second one is based on Microsoft Excel mesoscopic model by using of VBA programming language. So about microsimulations. Traffic surveys were done at each junction by authors this year for initial calibration. The main goal of the surveys was to create setting 1.0. These settings were considered as a baseline variant at each junction for the research. For each junction modeled in Vissim, 9 simulation scenarios were applied. These scenarios differ in traffic volume and in a headway time between bus services. Traffic intensity was increased up to 1.6 because we searched for more general results. At the same time, the value of bus headway time was adjusted from 3 to 10 and 20 minutes. During the simulations, a certain simplification was applied, as you can see at the bottom of the slide. We chose these to simplify the process on this more general level. Now let's turn to the second approach, mesoscopic simulation. Both models are based on scripts in Microsoft Excel developed by authors for this purpose. The first one is focused on general signalized junction. The model is based on cellular automation, and model contains signaling plans, priority in driving, public transport stops. The main reason for decision to develop this model is that the model is not dedicated to one specific case of junction, and it allows to create changes in parameters. The second one is dedicated to the type A stop. This model allows consideration of vehicle delay, queue length, as well as possibility to overtake the bus. We'll come to that later. About the general signalized junction, the key factor influencing the situation is the distance of bus stop from junction. Related simulation scenario is that the bus stop is moved in 9 steps by 10 meters. All other inputs are unchangeable to see impact of the distance. The second application is focused on the stop type A. It is an examination of the core effect that a bus standing and stop will block a driving lane. 3 simulation scenarios were applied. They differ in headway time between bus services and also different values of traffic intensity. Next point will be about results. Firstly, let's talk about bus type A. So if driving line is blocked by bus occupying the stop, an important aspect is what is the probability of the situation. Research of stop A can be extended by question whether is it possible to overtake bus at the stop. Drivers have 3 options: no stop, waiting, or overtaking. The figure shows that division of vehicles between waiting or overtaking depends on traffic intensity. Probability of overtaking decreases by rising volume of intensity. The opposite relationship applies to waiting. Each of 5 junctions simulated in PTV WISM was analyzed to know the ratio of delayed vehicles, which is percentage of delayed vehicles going through selected section. To see the section, see blue rectangle in figure. Comparing results from simulation scenarios is obvious. If we reduce bus headway time, the share of delayed vehicles increases. The great sensitivity to increase in traffic intensity was reflected especially in the Popkovice, which is black lines, and Praha, red lines. This is probably because the junctions with adjusted intensity approaching their maximum capacity. It is therefore clear from the figure that the share of delayed vehicles is influenced by both bus headway time and by the intensity of traffic flows. With this, we have come to the following topic, final methodology. Finally, the models want to quantify the proportion of when the queue of vehicles hits the junction and when it will be 0 or will be formed only behind the bus stop and will not affect other drivers passing through the junction. The turning point came with the compiled graph of depends of the stop's distance and the ratio of queues extended to the junction. The longer the busway head time is, the smaller the proportion is. With increasing intensity, the ratio increases more than with increasing bus headway time. So if it's needed to know the probability of moving the queue behind the bus to the junction, we have to know the traffic intensity, distance, and bus headway time. The resulting dependencies are shown in the following figures. Each figure is intended for a different value of the bus headway time, 3, 10, and 20 minutes. So whoever uses the methodology must first determine which value of bus headway time will be most appropriate. An example is the difference between the location in a quiet part of the city. For example, bus headway time is 10 minutes, intensity is 200 vehicles per hour, and the distance of stop is 10 meters from the junction. There is a probability of crossing the queue of vehicles into the junction almost 0. In contrast, the same location where the intensity is threefold. In this case, the probability is almost 0.7. So we can decide to move the stop farther away from the junction and reduce this probability. Value of the coefficient of determination in figures shows that with decreasing bus headway time, the methodology is more accurate. In conclusion, I'd like to say that distance of bus stops from junction was confirmed as one of the main criteria for methodology. Also, I had to say that the proposed methodology is a recommendation. It can provide a basic guideline for simple cases and cases needed to be decided quickly. It is also necessary to realize that the given dependencies apply according to the collected under specific conditions and chosen evaluation with simplifications. Thank you for your attention, ladies and gentlemen. Let me end by saying thank you for the opportunity to present this topic during this conference. This is all I wanted to say in my presentation, And now we have about 5 minutes for discussion.
Thank you very much. If there are some questions, please. Yes.
Good afternoon.
Good afternoon.
Thank you for the presentation. So I just have, I'm wondering about the software that you've used for the simulation. It's called Vism, and if there is a reason behind using it, you say that you used it for the microscopic simulation, as far as I understand. And if it's the same software that you use for the mesoscopic simulation, if you could say something about that. Thank you.
Actually, we used PTV Vism only for micro simulation, and for mesoscopic model, we used just Microsoft Excel.
So what was the reason behind using this specific software?
PTV Vism is only for micro simulation, and it's licensed software. We have approach to this software in our university, so it was a good chance for me to work with that.
I'm sorry, but if I don't know, is, for example, the simulation paradigm that is used for this software, is it, for example, an agent-based or a discrete event simulation models, or if it's maybe this simulation software is ad hoc software, for example, for traffic simulation or something like that? Is it correct? Okay, so what is the paradigm that you used for the simulation again?
Sorry, I didn't hear you.
Yeah, I'm sorry. What was the paradigm that is used for the simulation? Is it a discrete event simulation?
Yes, what kind of simulation? Is a continuous simulation or a discrete simulation?
It's continuous, and you can also you can see results at the end. But also, if you want, you can play a video of the simulation, and you can stop it and see every second of the simulation.
Thank you very much for the answer.
Mm-hmm.
Thank you, Zdeňka. And we continue with the third presentation, that is multicriteria evaluation of variance as a decision-making support within rail traffic simulations. And it's with Zdeněk, Novotný, and Antonín, Kavička.
Yes, thank you for the introduction. I'll try to play it. Just to make sure, do you see my shared screen with VLC player?
Yes, we can see it.
Okay, I'm sorry, I'm afraid I didn't share the sound. Good afternoon. My name is Zdeněk Novotný, and I'm going to present to you our recent research of using multicriteria evaluation of variance as a decision-making support within our rail traffic simulations. During the presentation, we will briefly take a look on the rail transport, formulate the need of automated decision-making support, and mention some approaches and tools we have exploited so far. In the end, the results will be discussed. The rail transport itself is nothing to really be introduced. It is an important part of many people's everyday life. In 2019, before the pandemic, 8 billion passengers were transported traveling over 415 billion kilometers just in the European Union, not even mentioning cargo trains. As the construction of a new railway is slow and expensive, it is crucial to utilize the current infrastructure as much as possible to satisfy the needs. A way of effective management of the railway is the operational control. It is short-term planning with, in this case, potentially high long-term impact. The ordinary way to deal with operational control is to let a professional decide. Such decision is based on a mid-term and long-term plan and the professional's personal experience. Humans can also decide even in unexpected situations, but their communication and collaboration is relatively slow and limited. Their opinion also depends on their physical and mental condition. An automatic control uses prearranged plans as well, supplemented by a decision-making support. Computers are capable of fast and complex communication and collaboration, providing quick and, if implemented well, safe decisions. In the recent research, we focused on management of delayed trains in a station. There are many reasons for a delay, including weather conditions, breakdowns, crashes, and the human factor. A delayed train may cause delays to other trains, creating a chain reaction which could result to an utter collapse of the whole infrastructure. To avoid this, it is necessary to allocate a track for the delayed train if it cannot use the default one. The allocation has to be quick, safe, and effective. The goal of an automated decision-making support is to minimize the overall delay of all trains while preserving the railway safe. As it would be difficult, expensive, and even dangerous to execute such experiments in the real world, it took place in the simulation tool Mesorail. The Mesorail is a mesoscopic railway simulator developed on our faculty for several years. The simulator is capable of simulating train arrivals, departures, and acquisition of track segments. Arrivals can be optionally equipped with delays. If a train's path is blocked, it triggers a decision-making support to find another way. If such support is not enabled, or if no other or better path is found, it stops and waits. There are numerous approaches of automated decision-making, such as static priority list, nested simulations, expert systems, or artificial neural networks, and more. In this particular research, as the title says, we focused on the multicriteria evaluation of variants. Simply put, the method utilizes predefined criteria which are used to choose the best variant at the point of triggering the support. A criterion is something we want, but we can omit it if needed. If something is really necessary, it becomes a requirement, which may always be met. In our example, a good requirement would be avoidance of crashes. A train simply shouldn't crash to another, even thought it would reach a platform faster. At the time of evaluation, the calculation would be fast. Also, the state of the system can be taken into account with the right selection of criteria. Of course, the definition of criteria and their weights have to be defined by an expert, so they are bound to be subjective. Sometimes it is better to ask multiple experts. For our problem with delayed trains arriving to a station, the chosen criteria are as follows. The criterion A is the platform availability, which means the support prefers a free track or a track which is going to be released shortly over these occupied by waiting trains. The longer is the estimated departure of a blocking train, the lower is the value of the criterion A regarding the track. Therefore, the criterion A attempts to allocate a track as fast as possible. The criterion B is the platform sufficiency. This means that the support prefers tracks which are not going to be occupied until the train's estimated departure. The longer would the train block other arriving trains, the lower is the value of criterion B regarding the track. So the criterion B attempts to minimize the delay caused to trains, which will arrive after the solved train. And finally, the criterion C adds a tendency to follow the original plan. It makes the support prefer the original track or a nearby platform over further ones. A variant, in this case, is basically any track which is available for the train. This creates multiple combinations of variants and criteria, which can be illustrated as a matrix. Criteria are assigned weights. In this case today, the SATIS method was utilized. Each variant is then assigned a value of each criterion, and these values are weighted according to the weight of the respective criterion and summed together. The calculation is further discussed in the full paper. Of course, the variant with the highest total value is considered the best. As I already mentioned, the experiments were executed in the Mazariel simulator. The method of multicriteria evaluation of variance was tested on a scenario of a small station called Zdice. The scenario utilized a real track occupation plan kindly provided by a Railway Infrastructure Administration of the Czech Republic. Although initial criteria weights were calculated on the basis of the SATIS method, multiple weight setups were tested to provide the best result. The methods of priority planning and nested simulations were tested as well to set some reference values. The used metric for comparison is the mean sum of weighted delay increments of all trains in the simulation, according to a directive of the local railway administrator. The best setup of criteria weights so far was 40% for track availability, 40% for track sufficiency, and 20% for platform distance. This shows that criteria A and B are nearly of the same importance, while the criterion C is not so useful in minimization of delay. The method of multicriteria evaluation of variance exceeded the priority planning in all setups. The method of nested simulations achieved even better results with just one nesting, but its calculations were really time-consuming. So, for a conclusion, the chosen method turned out to provide better results than priority planning. Although it didn't exceed the nested simulations method, it is necessary to point out that even with one nesting, the replications took significantly more time in case of nested simulations. Also, as we used some predictions in calculation of values of criteria, specifically for arrivals and departures, there is a possibility that the method could be further enhanced simply by providing a more accurate predicator. Thank you very much for your attention.
So, thank you very much. Do you have any questions? Yes, Paolo.
Hi, hello. Can you hear me?
Good evening.
Good evening, Idalia. Thank you for the presentation. Very interesting. I just wanted to maybe if the presenter can elaborate more on the evaluation criteria. How do you calculate basically that evaluation? Thank you.
Thank you, Paolo.
Good afternoon. I'm sorry, my Microsoft Teams crashed for me. Did you see my presentation?
Yes. Yes, it was fine.
Okay.
Just we have this question from Paolo.
Okay, could I ask you to repeat the question, please?
Yes, sure. So my question is, can you elaborate more on the evaluation? How criteria, basically the evaluation itself. How do you calculate the evaluation for the?
All right. There were 3 criteria. The first was the platform availability, which is basically the time to remaining to expected arrival of the train, divided by the expected departure of the blocking train, if there is any. And the criteria P, the platform sufficiency, is basically the expected arrival of the first train, which is approaching the first the same platform, divided by the time remaining to expected departure of the train, which is the solved. And finally, the criterion C is computed as 1 divided by the distance of the platform from the originally planned one, which is basically a count of hops between the originally planned platform and the other. So the nearest there will be will have the count of 2, and the farthest the more is the value divided, and these values are calculated for each variant, respective to each criterion, and the resulting values, the resulting metrics, let's say, each value is then weighted by the criterions weight, and all these resulting values are then summed together for the respective variant, which results in a value, just one value for each variant, the sum for all the criterions respective to the variant, and of course the highest sum of these, the highest value is chosen then. So this is basically it.
Yeah, thank you for your answer. Actually, if I understood correctly, at the end you mentioned of the presentation, you mentioned about the weights. That is like the 2 parameters. The first 2, they have both 0.4, and then the third one 0.2. But how do you attribute those weights?
The weights were originally calculated using SATIS method, which basically computes, which basically is evaluating from a professional, which in this case was me, to try it. And it's basically about prioritization of one criteria against another, doing it for each criterion against all other criterions, and this gives us some ratings which are then normalized, and there are some resulting values. It is called SATIS method, and I've got it further explained in my paper, and of course cited.
Yeah.
And I'm sorry. The other setups we tried were basically about experiments. We just tried other criteria to see which will provide the best results.
Yeah. Thank you very much.
Thank you, Paolo. You mentioned SATI criteria. So you mean that you used Q in theory?
I'm sorry.
Yes, in your presentation, you mentioned SATI criteria.
Yes.
So my question is if you used Q in theory or what criteria are used?
I basically used SATI's method for deciding the weights of the original criteria. I'm sorry, the original weight for the criteria using SATI's scale to compare criteria to each other. And then for the values of respective criterions regarding the variance, there were values computed as I already explained. So the SATIS method was basically used for determining the weights itself using the SATIS scale.
Okay. Well,
I don't know if I answered the question.
Yeah. Thank you very much.
Thank you.
Well, we continue with for the presentation. This simulation of computer vision-based sensor system for autonomous transport, and is with Ambuja, Bangalore.
Yeah, thank you for the introduction. I would please ask you to share the video if possible.
Sure.
Thank you.
Hello everyone, we are Ambuja and Professor Mihail Gorovets, and I'm here to present our work, Simulation of Computer Vision Based Sensor System for Autonomous Transport. As of late, we have seen incredible success in the field of autonomous driving. Famous companies like Tesla, Waymo, Pony AI, Apple, to name few, have done incredible progress in this regards. But why are they not on roads yet? Often, what these videos don't show are the challenges faced in the technology. According to one of the recent survey on Tesla, one of the main challenges for their fully autonomous cars to be on the roads are sensors and their inputs. Autonomous cars use large set of sensors to see the environment around them. A large set of data from these sensors are fed to the car's processing system to process this data using artificial intelligence and machine learning. To enable truly autonomous cars, the machine learning system has to be able to handle all these data without needing a human intervention at any instant. So in that case, simulation is a wise option when it involves large set of data and scenarios to be tested. The simulation model developed in our work is expected to reduce the entire complexity, time, and cost in comparison with actual experiments. And our goal of this work was to develop an algorithm and simulation model for the computer vision based sensor to detect and recognize objects in sight, measure its distance and speed of movement. The novelty in this work was to solve the perception problem and to evaluate the workability of the system, the simulated sensor. The developed system will be stationary, that is, it will be independent and will not be moved with reference to the moving object. Hence, the calibration could be done even after the installation of this system. All these reasons makes it enough to use camera as the only sensor. There are a few tasks performed to achieve this goal, like develop a suitable system structure and develop mathematical model and algorithm for object detection as well as speed estimation, test the simulation and discuss the results. As we know, computer vision and neural networks are the main basis of autonomous driving. Computer vision helps computer to interpret and understand the visual world, and deep neural network analyzes the visual imagery. Our algorithm in this work is built on the basis of you only look once. This is the structure of our proposed system structure. As of now, we wanted to check the workability of the system through simulation, but structure of any hardware sensor would look like this: a module with a microcontroller to do the computation and transmit the output through wireless transmission. This was the developed mathematical model for this work, where it involves these 4 steps. Our first step was to digitalization of bitmap image, detection of algorithm of bitmap image, and then estimation function, and feed in few parameters for these sensors. Speed estimation flowchart looks something like this. If the detected object is a vehicle, and if it is a vehicle, then it generates the tracking ID, it calculates the distance, updates this consecutive tracked points, and then speed is estimated through distance calculation formula within the algorithm. Few results obtained from the object detection looks like this as presented. We did a series of experiments to conclude if the present detection works well. So what we did was we took some simple images from the Google, where there's like no complicated background, like you see in this picture, like person, dog, and cat, and the algorithm was able to work fine. And you see the snippets of you from a video which was taken, and the object detection was done. Of course, I agree, this algorithm doesn't work perfectly well. As you see in this picture, it detects a bench, but then in reality, it was a wooden dustbin, but then the algorithm detected it to be a bench. So it does need some corrections or changes or the improvement. Like always, I would like to show you some results in this video. As you see in this video, we can see the person, a pedestrian detected, and a few cars on the roads. And we wanted to check this algorithm function in order to evaluate the workability of the system in different weather conditions. We used the fog filter and the night filter, and then tried to feed them to the algorithm to see if it is able to detect the images correctly. So as you see in this picture, for the fog filter, it worked well for up till 70% of the fog filter, but after that algorithm had some problems detecting the objects. And in this night filter, we had clear visibility. The algorithm did not have any problem until 60%. Sorry. So after that, it had a problem detecting objects. And coming to the speed estimation algorithm, we did a series of experiments to be able to realize the estimation. And one of this experiment was to track the object. We wanted to check if it has been really tracked or not. So this was a simple experiment conducted where we were trying to track a ball, and you can see those results. It works perfectly fine. The algorithm works well, and these are few speed estimation results presented here. You see 34 km/h and 43 km/h. In this picture, I would like to mention that speed estimation of few cars within ROI and outside the ROI. You see in the left picture, we could see at 22 km/h, this car lies within specified ROI in the algorithm. The specified region of interest was approximately around 3 cross 4 feet below the camera, and it works well only if the vehicle passes through that region. And other than that, if vehicles are outside that, it has problem detecting it. And in the right picture, you can see an interesting result where the car stops near the zebra crossing while pedestrians are crossing it. And this is a presented result, speed estimation result, where it is detecting the vehicle speed within the ROI. And this sensor finds different applications as mentioned, like surveillance for the safety or railway crossings for the disabled, and many few. And this is how I would like to conclude, where I would like to say that this algorithm and software of the computer vision based sensor works well, and it is able to detect the objects which are in sight, and it also was able to perform well for synthetic data. And one more main plus point was that it was developed in Ubuntu OS, which would be a great advantage to be used in most of the embedded computers. So thank you.
Thank you for your presentation, Ambuja. And if there are some questions. Well, I have one. What is the difference between this proposal and others that maybe were before this one?
In this proposal, I would say one main difference what we tried or tried to achieve was that in the present systems, there will be camera and few other associated sensors with it, like lidars or radars to support them with the location or to estimate few other criteria. But what we tried from this work was that just by the visual imagery, like just using the camera as a sensor, we should be able to detect the objects and then estimate their speed just with their coordinates. That was the approach.
And is very expensive to develop this or not? I mean, the cost.
Like I mentioned, we just wanted to check the workability of the sensor through simulation, and we were kind of able to achieve it. I'm really not sure how it would be if we start implementing it in like hardware. That is our next step. Let's hope how it goes. Yeah.
Okay, thank you very much. Yes, Mohayed has some questions.
Hi, good afternoon.
Hi, yes.
So one of the research trends that is emerging right now is the utilization of simulation and artificial intelligence, and basically, particularly, let me say, the computer vision could be used in what is so-called virtual commissioning. Could you relate your research with this, and what you would say about this?
I'm not much aware of virtual commissioning as of now, but as per my research, yes, simulation has found in most of the cases, it finds its way, like it is the most preferred option when it comes to such applications.
Okay, thank you. Thank you.
Well, thank you very much to everybody. And this is the last presentation. So thank you for your attention.
Thank you.
Thank you very much.
Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.
Bye. Bye-bye.
Goodbye.